In this video, I'm going to do an example on analysis of variance with completely independent groups, so what we call randomized design or completely randomized design. We will be introduced to two different approaches, one which we call the completely randomized design, and in that situation what you have is that the samples are completely independent of each other, so there's no relationship between them. And the second model that I will introduce you to is called randomized block design. Now, randomized block design would be the equivalent of the sort of match pairs problem, but we're expanding the match pairs now to not just two samples, but three or more samples or three or more populations. The analysis of variance addresses the issue or the question as to whether or not a set of three or more population means are the same or that they differ. And so rather than doing pairwise comparisons to find out if there is one mean that differs, we will do a single approach that takes into consideration all of the data that we have. And we do that by analyzing the variation in the samples to answer the question whether or not the means differ. In this approach, what I'll do is I'll actually work through a problem because there's some formulas to introduce, and then I will explain the concept after I've worked the problem. I believe in this case it might be a little bit better because if I have to take you through the formulas first, it gets a little daunting. So let's start with the problem. Here's the problem that we have. I'm going to actually look at problem number 15 on page 567 in our textbook, and I'm going to read it right here for you. Excuse me. So we have to test whether the mean time needed to mix a batch of material is the same for machines purchased or produced by three manufacturers. The Jacobs Chemical Company obtained the following data on the time in minutes needed to mix the material. So essentially you have three different machines, and the question is, do these machines operate at the same rate, or are these machines different? In other words, the mean time to mix a batch of product, is that the same or does that differ among the three machines? So we're going to actually do this particular test. So the data that we have is that we took 4 random samples, one sample for each machine, and then we measure the time it took to mix the batches, and then we have the sample data that we see in front of us. Excuse me. So the sample data shows for batch number 1, 20 minutes, 26 minutes, 24 minutes, 22 minutes, and so on. So now, do we have a difference between the means? If we only had two populations, then all we would need to focus on is the difference between two means, whether or not we're talking about unknown standard deviations or known standard deviations. In this case, of course, we don't have the population standard deviations, so therefore we have to make an assumption about the population standard deviations. In this case, we're going to make the assumption that the population standard deviations are the same. They're all equal to a constant value, sigma. That is essentially, I'm going to assume that sigma 1 for population 1 is equal to sigma 2 is equal to sigma 3. So all of them are the same for this particular problem. And of course, the other assumption is that the samples were randomly chosen. So how should we approach this problem? We said that we're going to approach this problem by looking at the analysis of variance, okay? So let's state our hypotheses. Start off with a HO. So in HO, we will assume that the means are the same. So mu1 is equal to mu2 is equal to mu3. The means are the same or the means differ. HO or HA, sorry. The means differ. All right, so that's the first thing. Sorry. So the means differ. It doesn't mean that all of them are exactly different. At least one of them differ. So that's the first step. Second step is our test statistic. Now we are going to introduce you to a new distribution called the F distribution. And so test statistic. So the test statistic is F, new distribution, which is given by the ratio of two variances. So that's how this distribution is created. It's a sampling distribution of the ratio of two sample variances. So if I take two samples from two different populations and I take the ratio of those sample variances and I keep generating pairs of samples from the populations, that distribution that I will get will be called an F distribution. And so I'm going to need the following: MSTR over MSE. MSTR is the mean squared due to treatments and the mean squared error. Now when we say treatments, what are we talking about? So we'll start using the language of treatments or groups. Treatments, basically in this particular problem, the treatments would be the different machines. So I am doing this experiment and one treatment is machine 1, one treatment is machine 2, another treatment is machine 3. Or I could call them groups, group 1, 2, and 3. So you may hear me go between treatments and groups. And what we have is that the ratio of the two variances, and I will show you later on how those two values are variances, is the ratio of the mean square due to the treatments. So we're looking at the variation from treatment to treatment versus the mean squared error. And that mean squared error is the variation within each of the treatments. So in other words, if we look within each sample and see how do the numbers vary for machine 1, what kind of variation there is in machine 2, what kind of variation there is in machine 3, then we refer to that as the error. And so that's the formula. Another thing that we need is that we need two different degrees of freedom. The numerator has a degrees of freedom, which we'll call df1, and the denominator has a degree of freedom, which we'll call df2. So it turns out that df1, the numerator degrees of freedom, is k minus 1, where k is the number of treatments. So in our problem right now, the number of treatments would be 3 machines. 3 minus 1 would be 2. So that would be k equal number of treatments. All right, number of treatments. And then the denominator degrees of freedom, that's the one associated with MSE, we call it df2, would be the total number of values that we have. We could call it NT according to your text, which is, in this case, we have 3 samples of 4 each, 4 3s are 12, minus K. And that we know the NT is total sample size. The total sample size, okay? That's all of the values that you have across all of your different samples. It's kind of like adding up n minus 1 plus n minus 1 plus n minus 1. So in this case, n1 minus 1 plus n2 minus 1 plus n3 minus 1. Well, n1 plus n2 plus n3 gives us the total, which is nt, and the minus 1 plus minus 1 plus minus 1 gives us the k. So in other words, there's 1 for each treatment. And so it becomes nt minus k, because we're looking at the variation within the different samples. Okay, so that's step 1 and that's step 2. Step 3. Step 3, we need a decision rule. So the decision rule, the F distribution actually kind of looks like the chi-square distribution. It is skewed, and it's always a right tail test for us. So this is alpha, 0.05, and we need the degrees of freedom. The degrees of freedom before we find this. So here's our F critical, which in this case is F alpha, degrees of freedom 1, degrees of freedom 2. So this particular distribution will look a bit strange as well to us, because of the fact that we now need these two different degrees of freedom and the area in the tail to find the critical value. So when you look up the F distribution, you'll notice that we have several pages that we have to flip through sometimes to get a critical value. I will show you that. I'll demonstrate that for you a little later on. Now, I did not predetermine the critical value. I should have, but I'll find it for you later, and I don't want to pause the video. So what I'll do is I'll use the p-value rule. If the p-value is less than 0.05, we will reject HO. All right? That's how we will do that. And I'll come back to the critical value very shortly. Let's see if we could kind of introduce here. Maybe I might be able to introduce the... I'm looking to see if I could find the let's see what we get. I should be able to introduce it right here. Why not? So if I go to my drive and I go to our stats course, which is somewhere here, and we need our tables. Here we go, statistical tables. And here's the F table right here. So I want to add that. Bear with me for a quick second. So there we go. That's what the F table looks like. And if you look at this, you'll notice that the two different degrees of freedom. Let me just sort of expand that a little bit. So denominator degrees of freedom, which is on the left side. That's our denominator degrees of freedom right here. And our numerator degrees of freedom is here on the top. Numerator degrees of freedom. So in the particular problem that I'm looking at, we have excuse me, so in that particular problem that I'm looking at, the numerator degrees of freedom would be k minus 1, which is, we have 3 treatments, minus 1, which would be 2. So I'd have to look over here. And the denominator degrees of freedom that I'll be looking at would be 9, which is NT, which is the total number of values that I have, which is 12, minus the 3 treatments that I have, which is, 3. So 12 minus 3 gives me 9, which means that I have to look over here. Now, I notice that my table only goes to 5, but remember I mentioned to you there's several pieces of this table. So I have to continue looking at the pages. Let's go to page 2. Let's see. Here's 9 right here. So I'm looking for 2, 9. And the area in the tail, in this case, is 5, right? So look at where we find the area in the upper tail. Area in the upper tail wow. I'm gonna have to edit this video for sure. If I could clear my throat. This is not good. So, so the area in the upper tail, so I had to flip a page, and here is the value that I'm looking for, the critical value. So if you look, you'll see the degrees of freedom, 9 is right here. The numerator degrees of freedom, 2 is here. So which means that the value that I'm looking for, my critical value, is in this batch right here. Let me expand that for you to see. It's in this group. So how do I know which value to pick? It depends on the area in the tail. The area in the tail is actually given to us right here. And because the area in the tail is 0.05, then my critical value is 4.26. All right, so now this basically takes chi-squared and t, we kind of use them very similarly. In this case, is also kind of similar, except that we have 2 different degrees of freedom. So now what we have to do is to find the the numerator degrees of freedom, the denominator degrees of freedom, and the area in the tail. So because this would lead to many tables, because there's so many different, so the degrees of freedom for the numerator can go from 1 to a large value, then denominator degrees of freedom from 1 to a very large value. So it means that we would have to, for every area in the tail, we would have to generate a massive table. So what our book does, it just picks a subset or a small number of areas in the tail from 10%, 5%, 2.5%, 1%, and then gives us values for those. Of course, Excel can give us the exact value if we wanted that. So that's my critical value right there. So let me go back to my problem. I mentioned a little bit earlier that I didn't have the critical value, but now I do, which is 4.26. So 4.26 is our critical value. So I could also state if F observed is greater than 4.26, we will reject the null hypothesis. So if the observed value of F is greater than or equal to 4.26, reject the null hypothesis. All right? So that's our decision rule. Now the fun begins when it comes to having to calculate those values, and this is where the formulas gets introduced. Okay, so now we will go through and do our calculations. So here's what I recommend that you do in terms of your approach. You can see it here in my problem setup. What I would recommend that you do is this. Take each of the samples and find the sum of the x's for the samples. So you can see here the sum of the x squareds. And why do I need sum of x and sum of x squared? Because I'm going to need the sample mean, which is basically the sum of all of the x's divided by n, in this case divided by 4. So 92 over 4 gives me 23, 112 over 4 gives me 28, 84 over 4 gives me 21. And then I need the sample variance, which is S1 squared, S2 squared, S3 squared. I need those values, right? Sample variance. S1 squared, S2 squared, S3 squared. So that's what those values are. Sample variance. Excel can of course calculate all of them for you, but if you're doing this by hand, you will need to calculate the sample variance. And you recall, to calculate variance, S squared, we need SSX over n minus 1, where SSX is equal to the sum of x squared minus the sum of x all squared over n. So of course we will need the sum of x squared, which is given, which is right here. Then we will need the sum of x, which is right here. So we have the values to get SSX, and dividing SSX by n minus 1, I should say nj minus 1 in this case. If we're doing that for each sample, and that will give us the sample variance. Okay, so now we have the sample mean, the sample variance, and we have the sum of the x's, sum of the x squares, which we need to be able to calculate the sample mean and the sample variance. So I'm going to just sort of set up this problem over on the other side as well. So I don't think I need to really show you the computation for that, because we know how to find a sample mean and we know how to find a sample standard deviation. So it's important for us to find those values that I have here. So I'm just going to use them, and in step 4. So let's go back to step 4. In step 4, we do the analysis, and we're going to want to calculate our f value, which is MSTR, mean square due to treatments, over MSE, which is the mean square due to the error. Now, the mean square due to treatments, MSTR, is given by SSTR over K minus 1. So that's a sum of squares over the degrees of freedom. And that's why it's a variance. If you think about the sample variance S squared is SSX divided by n minus 1. Well, what is SSX? SSX is the sum of squares due to x, and then n minus 1 is the degrees of freedom. In this case, SSTR is the sum of squares due to treatments divided by degrees of freedom K minus 1. And so, therefore, that gives us a variance. Now we want MSE. MSE is equal to SSE divided by N, excuse me, NT minus K. So SSE is the sum of squares due to the errors. Again, sum of squares. And NT minus K is the degrees of freedom, the denominator degrees of freedom. So that also a variance. Hence you could see why this formula is a ratio of 2 variances, which gives us an F value. So let's look at the formulas for SSTR, and those are in your text. So SSTR, the sum of squares due to treatments, is NJ times X bar J, that is the mean of treatment J. Subtract the overall mean, that is the mean of all of the values, and we square that, and then we add them all up over J. So that will give us the sum of squares due to the treatments. When I divide that now by K minus 1, that will give me MSTR. So for our problem, this would be N1 times X bar 1 minus X double bar plus N2 times X bar 2 minus X double bar, which is the overall squared, plus N3 times X bar 3 minus X double bar squared. So that gives us the SSTRs that we're looking for. Now I should show you that I went ahead and calculated the sum of the x's, sum of the x squareds, the sample mean, and the sample variance. We're going to need that for this problem. So I would urge you, when you solving this problem, to go ahead and find these values very early. So now let us compute the values. So we want SSTR is equal to, in this case, N1, which is 4. Well, I should tell you that the overall average, X double bar, when I add up all of the values and then divide by 12, if I sum all of the values, it becomes, let's see, 92 plus 112 plus 84. What does that become? Let me just use my calculator very quickly. 92 plus 112 plus 84 equal, so 288 divided by 12. So 288 divided by 12 gives us 24. All right. So here we go. So that's equal to 24. Equal 24. All right. So let's find SSTR. SSTR would be 4 x bar 1, which is 23. 23 minus 24 squared plus 4 times 28 minus 24 squared plus 4 times 21 minus 24 squared. Okay. When we compute this, this turns out to be 104. So therefore MSTR, which we know is equal to SSTR over K minus 1 is equal to 104 divided by K, which is 3 minus 1. That gives us 52. So that's our MSTR right there. Now let's move to SSE and MSE. Let's find those. So we want SSE. It doesn't look right. So SSE is equal to NJ minus 1 times SJ squared. And then we have to add them all up over J. So in our case, it would be N1 minus 1 times S1 squared plus N2. I don't know why my thing is not writing properly. N2 minus 1 times S2 squared plus N3 minus 1 S3 squared. Alright? So from our data, we would have 4 minus 1, which is 3. So 3. Or maybe I should let me just leave it as 4 minus 1, so at least you know where it came from. 4 minus 1 times 6.67 plus 4 minus 1 times 4.67. So these are the sample variances that I calculated earlier. Plus 4 minus 1, that's for the third treatment, times 3.33. Alright? Now when we compute that, we get 44.01. I believe that's 44.01. Let me just verify that. Yes. And so MSE is SSE, the sum of squared errors, divided by degrees of freedom, which is NT minus K. NT is 12, so it would be 44.01 divided by 12 minus K, the number of treatments, 3, it gives us 4.89. So that would be MSE. And now we could actually calculate now our F value, F statistic. So F, we know, is equal to F observed MSTR divided by MSE, and that is the 52 divided by 4.89. What do we get? 52 divided by 4.89. 52 divided by 4.89 is equal to 10.63. 10.63. So now if we're using the critical value approach, you can see 10.63 is in fact much larger than the critical value that we found, which was 4 point something. If I go back, let's see, what was our critical value? 4.26. So our critical value is 4.26. If F0 is greater than or equal to 4.26, we will reject the null hypothesis. So let's keep going. So we have 10.63. Let's find the p-value. P-value is fun with this distribution. All right. So let's see. I'm going to move this up here. So p-value by definition is the probability of observing the sample value or a value that's even more extreme. So our p-value in this case, p-value or probability value is pf greater than or equal to 10.63. So if you thought finding probabilities with the t-distribution or chi-squared was fun, this one is even more fun. And so let's see what we will do with that one. All right. So we want to find the area in the tail for 10.63. And what we're going to need to do is to go to our F table. Now remember that the numerator degrees of freedom is 2, the denominator degrees of freedom is 9, so I must go to 2, 9. And here's my 2, 9 right here. In case you're not convinced, here's my numerator degrees of freedom up here, 2. Here's my denominator degrees of freedom on the left, which is 9. And so therefore the values that I'm looking for is over here. Now what you will notice is that if my F statistic was 3.01, the area in the tail would have been, let me just circle that, 10%. Remember, these are the areas in the tail right here. So if it was 3.01, the area in the tail would have been 10%. If it was 4.26, the area in the tail would have been 5%. If it was 5.71, the area in the tail would have been 0.025. If it was 8.02, the area in the tail would have been 0.01. But I'm looking for 10.63. So if I keep going, what's happening to the area in the tail? The area in the tail is getting smaller. And so therefore, my p-value will be less than 0.01. Okay? Because to get to 10.63, the biggest I have now is 8.02. I have to keep coming down. All right? So, which means, when I go back here, that this is less than 0.01. So as you can see, I will end up rejecting the null hypothesis anyway. 10.63 is greater than 4.26, and 0.01 is less than 0.05. So to finish up, step 5, decision conclusion. All right, so we have, since 10.63 is greater than 4.26, that's critical value approach, or since the p-value is less than 0.05, which, of course, because it is actually less than 0.01, I should actually just state less than 0.01. We reject HO. What do we conclude? At least one of the means differ. We conclude the means are not the same. All right? We conclude that the means are not the same. Can we be wrong? Certainly we can be wrong. What's the risk of being wrong? The risk of being wrong is type 1 error, which is less than 0.01%. So possibility of type 1 error. Okay, possibility of type 1 error. And we have that probability of type 1 error. The probability of type 1 error, we know is the p-value is less than 0.01. So that answers the hypothesis testing question for the case when we're dealing with completely randomized design. Okay, that completely randomized design assumes that each of the samples are different or independent of each other, and so therefore we have to use this process where we calculate the mean square due to treatments, the mean square due to the error, and then we take the ratio of those two values. We use an F distribution because an F distribution represents the ratio of two sample variances, and we found that the test statistic was 10.63, but our critical value is 4.26, in which case we ended up rejecting the null hypothesis. Now, immediately we don't know which of the means different, right? And there is a procedure called the LSD procedure, Fissures Lsd procedure. I want to introduce you to this because a lot of the questions in MindTap actually ask you to do Fissures Lsd. So it's called Fissures Lsd, and LSD stands for least significant difference. The least significant difference is basically looking for the pair of means that have the least significance in terms of the difference between them. In other words, to identify the mean that's different, what we have to do is we have to take pairwise comparisons of the means, take pairwise differences, and actually compare them to a value which we call the LSD. So in essence, what we're doing is we're working with this kind of idea. We will take the absolute difference between a mean I and a mean J. So we just want to know what's the magnitude of the difference. And then what we're going to do is to compare it to, LSD. All right, what is LSD? So we already said it's least significant difference. We calculate the LSD by the following formula. It becomes T alpha over 2 degrees of freedom T alpha over 2 degrees of freedom, and you multiply that by square root of MSE 1 over sample I plus 1 over sample J. Now if you look at that, that looks like the margin of error of a confidence interval, and that's exactly what it is. So in essence, for you to find a difference between two values, the magnitude of the difference must be larger than the margin of error. Think about it for a second, right? Remember when we did confidence intervals for difference between means, we would find a difference as long as the margin of error was actually smaller. So for example, if I say the difference between two values, two population means is 4 plus or minus 2. Well, what will happen is that would be the difference between those two means, mu1 minus mu2, will be between 6 and 2. But let's imagine the margin of error was actually bigger. If the margin of error was bigger, if I made the margin of error bigger, I made it 4 plus or minus 6, then what happens is that I will end up with a negative difference, and that negative difference means that the difference between the two means can possibly be 0. So if I go, this would be mu1 minus mu2 would be 6 plus 4 is 10, but 4 minus 6 is negative 2. So in that case, the interval will contain the 0. So if you don't want the interval to contain the 0, because remember, anytime the interval for a difference contains the 0, it is possible that the two population means can be the same. So if you don't want that, it means that your point estimate of that difference must be greater than the margin of error. So that's essentially what we are looking at here, is that the point estimate, doesn't matter if you take a negative difference or positive difference, I minus x bar j, that point estimate must be greater than the margin of error, which we call LSD. And that's how we compute the LSD. So let's just test the difference between x bar, or not x bar, but mu1 and mu3, whether or not those two means differ. So if we do this, let's add a new page. Let's calculate. So now we're going to test whether or not there's a difference between mu1 and mu3. So is there a difference between mu1 and mu3? All right. And so here we go. And the reason why we actually picked those two is because x bar 1 was 23 and x bar 3 was 21. So those two were kind of closer together than x bar 2, which was 28. 28 was a bigger gap between 23 and 28, and also a big gap between 21 and 28. So then we want to check to see whether or not x bar 1 and x bar 3 are significantly different as well. But we know that there is a difference already. We already proved that. And it's likely that mu2 is the one that's different from the rest. But we also want to check whether or not mu1 and mu3 are different from each other. And so x bar 1, the absolute value, x bar 1 minus x bar 3, gives us absolute value of 23 minus 21. Sorry, which is basically 2. Let's find LSD. So we need the difference of, we need the t value, our critical t value, t.025, right? And if we look at t.025 with the degrees of freedom, in this case, which will be n1 plus n3 minus 2. So to be for 8, it will be 6. We will get a critical value of 2.262. So 0.025, because we are going to, the reason why we are using 0.025 is because alpha is 2, right? Sorry, alpha is 0.05, sorry. So it's like a confidence interval, so we use alpha over 2, 0.025. 0.025. And so that 0.025 with the degrees of freedom, which is, I need to now look at the t distribution for me to find a critical value. This is 0.0256, which gives us a critical value of 2.262. So now we find LSD, which is 2.262 square root of MSE, which we already found, 4.89, 1 over 4 plus 1 over 4. All right? And then it turns out that that value is 3.54. So notice that the absolute difference 2 is not larger than 3.54, which means that mu1 and mu3 are not different from each other. Or at least we cannot show that they are actually different from each other. So we could say, since 2 is less than 3.54, we cannot conclude mu1 and mu3 differ. Okay, and so the one that's really different from the rest, since mu1 and mu3, we're not saying that they're the same, but they don't differ, but we found a result that said that the means differ. So clearly there's only 3 means. So the one that has to be different has to be mu2. So mu2 is the mean that is different. All right, so I hope you get that. So essentially we show mu1 and mu3 are not different, but we did prove in our hypothesis test that the means are different. So which mean then is the different one? If mu1 and mu3 are not different from each other, so mu2 has to be the odd one out. And so that's Fissures' least significant difference process. And you could kind of create a spreadsheet for that very easily. Last thing I want to show you is that in step 4, while I showed you the calculations as I did, I want you to learn to develop this Anova table. It's very important. So an Anova table. The Anova table looks like this. Sources of variation, SOV. The sum of squares. That doesn't look like SS. SS, sum of squares. The DF, the degrees of freedom. MS, the mean square. And then we get the F value and the F critical. And then P value. So what's the sources of variation? We say treatments. So the SS for treatments was 104. For error, we found an SS of 44.01. And then if we actually total that, we would get 148.01. That we would call SST. Sum of squares total. The degrees of freedom was K minus 1 for treatments, so which was 2, but NT minus K, which was 9. When we add them together, we get 11. So that's basically how you get the overall N minus 1. If for the overall set of samples, when we group them together, and then that is essentially 12 minus 1, which is 11. So then now to get the MS value, remember an MS value, mean square, is the sum of squares divided by the degrees of freedom. So 104 divided by 2 will give us the 52 we were looking at, and the 44.01 divided by 9 gave us the 4.89, I believe it was, that we were looking at. Now the F value is the MSTR divided by MSE. So I must now divide those two values to give me my F observed, which is basically the 52 divided by 4.89, and we got 10.63. Now with our critical value, we found that from the table, which we know was 4.26, and the p-value, which we know is less than 0.01. So that's just a way of summarizing everything neatly, and in step 4, that's kind of what you want to achieve, to show this quite nicely. And you could see here that our F observed, 10.63, is larger than 4.26. But we also know that alpha is 0.05 for this question, and our p-value is less than alpha. So that is the Anova table, which I want you to kind of get used to. Okay? So on that note, that covers the analysis of variance with completely randomized design. To understand the logic behind all of this, it is, so as you can see, this problem is a bit involved mentally, but once you do a few examples, the process gets pretty, routine. However, I just want you to understand what is involved here in terms of the logic behind the model. So the idea really begins with this: if all of the means are the same and they all have the same variance, so basically there's just a single population, but we take in random samples from each one. If we take this sample and we got X bar 1, and we got another sample X bar 2, another sample, x bar 3. So what happens is that with these samples that we have, the population has a standard deviation sigma, or variance sigma squared. What we can do is we could try to calculate an estimate of sigma, and we do that by using MSTR. That's what MSTR is. So we say, well, let us find the overall mean of the 3 samples, which is x double bar. Let's say just somehow it falls between those 3 somewhere around here. Let's just put it here somewhere. No, that's probably not right, but anyway, let's just put it here, for example. So the idea is that we want to use the variation across the group. So as you can see, each of these sample means are different from the overall mean. So of course, x double bar is an estimate of mu, the population mean. But as you can see, there's a difference between each of those, right? So there's variation across the groups. And what happens is that we could actually use that variation to estimate sigma. And that's where MSTR comes in. So if we take MSTR, we look at the variation from each mean and that overall mean, we square it, add it all up, but we also have to weight by the sample size as well. That's SSTR, that's the sum of squares, and if we divide by k minus 1, that gives us an estimate for sigma. What happens is that when the means are from the same population, and that means that generally speaking that they will be closer together, the estimate of sigma tends to be what we call unbiased or very tight, a very good estimate. But if it so happens that those means came from different populations, you know, if came from different populations, if they came from here, here's the other one right here, and this other one right here. So if they came from different populations, what happens is that the estimate MSTR of sigma is a very bad estimate. It tends to overestimate the value. Okay. Now, so essentially we're trying to estimate sigma for the population, and we use MSTR as one estimate of that. The second estimate of that is to take the MSE, the mean squared error, MSE. And the mean squared error is sort of, it does not, if you assume the population standard deviation is the same, it is not as sensitive to whether or not the means come from different populations at all. It is basically just looking at the variation within each of the samples, right? That's all we're looking at. We're measuring the variation within each of the samples. So when we get SSE over NT minus 1, the overall, so in other words, NT minus K, sorry, NT minus 1. In other words, this is giving us a variance, and that variance is estimating, well, I should put sigma squared over here. Not estimating sign, but MSTR is a variance, so it's estimating sigma squared. And this here, MSE, is also a variance, and also estimating this. It turns out that the estimate MSE of that value is fairly stable, so it does not change a whole lot. But MSTR is the one that's sensitive to whether or not it's from the means are from different populations or they're from the same population. So what tends to happen is that because MSTR, when the means are from different populations, overestimates the population variance, sigma squared, so MSTR will tend to be larger than MSE. And so the more that we have evidence that the means are from different populations, the bigger our F value will be. MSTR will be a bad estimate of the population variance, but it will overestimate it, much bigger than it needs to be. compared to MSE. So that ratio will tend to be greater than 1. And if it's sufficiently greater than 1, a lot greater than 1, like in this case it was 10 times greater in this last example we just did. So it was a bad estimate, 10 times greater, and so therefore we had to conclude that the means were not all the same. But when the means are pretty much all the same, we will get values that are closer to 1. Not exactly 1, but closer to 1. In other words, they will fail to exceed the critical value. All right? And so that's essentially the logic behind this approach, is that in essence, what we're trying to do is to estimate the population variance. We use the variation across the different treatments to estimate that. And if the treatments are from different populations, then the estimate of the population variance, sigma squared, is usually overestimated. All right? But then if it is an unbiased estimate, it tends to be, a pretty good estimate, a pretty tight estimate, and it should be closer to MSE, which is also another estimate of the population variance. So when those two are close, great, we cannot reject the null hypothesis. But when they are much further apart, that's when we get the evidence to reject the null hypothesis. All right. So on that note, I hope that we get a sense of analysis of variance for completely randomized design. When it comes to randomized block design, we just add one additional wrinkle to the problem, but the basic concept is the same. All right? Good. Thank you.